Welcome to the IPv6 Fundamentals module, which gives a description of IPv6, focusing on IPv6 address types, interface configuration, and routing configuration. The module also compares IPv6 with IPv4 and explains the process of tunneling IPv6 traffic over the IPv4 network. This module will help you familiarize yourself with IPv6, an important next-generation protocol used in networks today. At the end of this module, you will be able to describe some differences between IPv4 and IPv6, list IPv6 address types, describe the IPv6 addressing format, enable an interface for IPv6 operation, configure and monitor routing for IPv6 environments, tunnel IPv6 traffic over an IPv4 network. IPv6 is a next-generation protocol designed to eventually replace IPv4, which is used primarily in networks today. Defined by the IETF, IPv6 is seen as a redesign of the IPv4 framework, primarily due to the depletion of available IP addresses. As early as 1980, there was an experimental protocol named Internet Stream Protocol, or ST, that was considered by some to be Internet Protocol version 5, but ST was never officially known as IPv5 and never passed experimental stages. Although address exhaustion was a major reason for the development of IPv6, several other issues exist that IPv6 attempts to resolve. It also contains a number of other enhancements. Click each IP version to learn some of the differences between IPv4 and IPv6. Some benefits of IPv6 are more efficient routing, quality of service, or QoS, elimination of the network address translation or NAT requirement, network layer security with end-to-end IPsec, ease of management using stateless address auto-configuration or SLAAC, and improved header format to reduce header overhead. IPv6 headers include improvements over IPv4 headers that provide simple, more efficient processing. Where IPv4 has a 40-byte field set aside for special options, IPv6 supports extension headers that can be appended to the IPv6 header to support additional options. The IPv6 header has a fixed length of 40 bytes and includes fields as shown in the diagram. Note, this structure of IPv6 is a result of removing several IPv4 fields, such as header length, identification, flags, fragment offset, and header checksum. Click each field in the diagram to learn more. IPv4 headers and IPv6 headers share several characteristics. For example, the version, source, and destination fields from IPv4 were carried over to IPv6. One of the biggest differences between an IPv4 packet and an IPv6 packet is that if IPv6 needs to fragment a packet, it uses extension headers to do so. Several fields from the IPv4 header were dropped in favor of a more streamlined, efficient header. Because the IPv6 header is always a fixed size, the header length is no longer necessary. If a packet requires fragmentation, extension headers will take over the process using Path Maximum Transmission Unit, or Path MTU, discovery. Some fields in the IPv6 header moved from their previous locations in IPv4. For example, the Type of Service, or TOS, field was replaced by the Traffic Class, or TC, field. The Time to Live, or TTL, and Protocol fields were also renamed and moved in IPv6. The Flow Label field is a new field in IPv6. As mentioned previously, the IPv6 header was improved with faster packet processing in mind. Because the IPv6 header has a fixed size of 40 bytes, the options that were once included inside the IPv4 header are now appended to the IPv6 packet using extension headers. 6 extension headers can be used in IPv6. Click each extension header to view its description. In April 2009, the American Registry for Internet Numbers, or ARIN, sent a letter predicting complete IPv4 address exhaustion by 2011 and warned all organizations to begin planning for IPv6 adoption. Other regional Internet registries, or RIRs, made similar predictions. The ARIN announced on September 24, 2015, that its free pool of IPv4 addresses was depleted. The escalating demand for IP addresses and the possibility of exhausting IPv4 address allocations was the driving force behind the development of IPv6. As opposed to the 32-bit address space of IPv4, IPv6 has an enlarged address space of 128 bits that can potentially support 2 to the power of 128 addresses. In comparison, IPv4 uses a 32-bit address supporting approximately 4.29 billion addresses. If 2 to the power of 128 doesn't sound like a big number, think of the number of available addresses in another way. Enough IPv6 addresses exist to supply about 2 to the power of 95 addresses for each person on Earth, or about 2 to the power of 52 addresses for each observable star in the known universe. You should be familiar with the 3 types of IPv6 address that exist. Click each IPv6 address type to learn more. At first glance, an IPv6 address can look alarmingly complicated. IPv6 presents a 128-bit address in 8 16-bit hexadecimal blocks separated by colons. However, IPv6 does allow for abbreviation. Consider these examples. You might think that you are looking at 3 different IP addresses, but in fact, you are looking at the same address in all 3 examples. 4 consecutive zeros in an address can be identified as a single zero. You can omit leading zeros from the notation. Note, a double colon can replace consecutive zeros, leading zeros, or trailing zeros. However, you cannot use a double colon twice in an address notation. Doing so will result in the misinterpretation of the IP address. IPv6 has some similarities to IPv4 in text presentations. The prefix determines the network address or subnet. The example shows a 64-bit prefix. The prefix is noted as shown in the inverted pyramid. As in the case of IPv4, certain prefixes are reserved and used for specific types of traffic. RFC 4291 defines the latest rules regarding prefix notation. Click the Example button to view a few examples of prefix notation. Similar to IPv4 nodes, IPv6 nodes must receive IP address assignments from their ISP. ISPs find information about their regional registries to verify if an IP address is in use. Address allocation is a work in progress, but RFC 3177 specifies a few rules that you should follow, which are shown here. The ::/16 prefix is reserved for special addressing. There are 2 types of special addresses, the unspecified address and the loopback address. Click each address type to learn more. IPv6 addresses have scope, which identifies the application suitable for the address. Unicast and multicast addresses support scoping. Unicast addresses support two types of scope, local scope and global scope. Addresses with local scope are used within the same routing domain. Addresses with global scope are used between routing domains. Link local unicast addresses are used within a single network link. The first 10 bits of the prefix identify the address as a link local address. Link local addresses cannot be used outside a network link. Multicast addresses support 16 different types of scope, including node, link, site, organization, and global scope. A 4-bit field in the prefix identifies the scope. The link local unicast address is identified with the binary prefix 1111111010, followed by a string of 54 binary zeros, the host-generated interface ID, and a 64-bit mask. Any host automatically generates this address on all its IPv6 interfaces. Because the first 64 bits are the same for every link local address, this address is guaranteed to be unique only on an individual subnet, and could be duplicated by hosts on other subnets. Because the bits are the same for every link local address, link local addresses are never routable. Interfaces configured for IPv6 automatically generate a link local address. This address is often used for neighbor discovery, auto-configuration, and routing protocol traffic. Link local addresses were designed to provide automatic address configuration for small networks with a single subnet. Similar to IPv4 public addresses, global unicast addresses are globally unique and are used to connect to and route through the Internet. These addresses are identified by 4 different fields. Click each field in the diagram to learn more. The interface ID is a 64-bit field that uniquely identifies a host on a subnet. On Ethernet interfaces, it is a permutation of the MAC address associated with the interface to which the address is assigned. The interface ID is expressed in the IEEE Extended Unique Identifier 64 or EUI64 format. Because the host can determine the subnet to which it is connected by router advertisements, and can generate its own interface ID, IPv6 addresses are easy to configure automatically on any host. The address needs additional bits to widen it to the specified 64-bit length because Ethernet MAC addresses are only 48 bits long. To obtain an Ethernet interface ID, concatenate the first 24 bits of the MAC address or company ID with binary value 11111111111110 or 0xFFFE, and the remaining 24 bits of the MAC address or manufacturer extension ID. EUI64 addresses set the universal or local bit to a value of 1 to signify that this address is globally unique. The universal or local bit is the next to lowest significant bit of the first octet of the address. For example, the Ethernet MAC address 00:10:A4:A6:69:D0 would generate an interface ID of 00:10:A4FF:/FEA6:69:D0. Assigning an IP address to the many devices of your network is one of the most important tasks in network management. In IPv4, address assignment is managed using 2 different methods. The first method is to statically assign an IP address to each device. This method is efficient only if the network is small and you do not plan to change IP addresses frequently. The second method is to configure IP addresses automatically using the Dynamic Host Configuration Protocol, or DHCP. With DHCP, a device that requires an IP address contacts the DHCP server and automatically receives an IP address. Although DHCP is considered easier to manage than statically assigning an IP address to a node, you must configure and maintain the DHCP servers. Static IP address assignment and DHCP are considered stateful configuration methods. One of the enhancements to IPv6 is the implementation of stateless auto-configuration. Stateless auto-configuration enables IPv6 nodes to automatically assign an IPv6 address to a neighbor, effectively eliminating the need for static address assignment and DHCP. An administrator can still use stateful configuration methods if necessary. Stateless auto-configuration consists of several elements. Scroll through the panel to learn about each element. Neighbor discovery, or ND, is the process of tracking the reachability status for neighbors in a local link. Defined in RFC 2461, several enhancements were made to ND since IPv4. ND combines and improves upon Address Resolution Protocol, or ARP, and Internet Control Message Protocol, or ICMP, router discovery, and redirects to detect whether or not neighbors are reachable. A device views a neighbor as reachable when the device receives recent confirmation that the neighbor received and processed IP traffic or neighbor solicitation, or NS, requests. Otherwise, the device considers the neighbor unreachable. An IPv6 router with ND enabled can send ND information to downstream nodes. ND is optional on IPv6 devices. Consider this example. 5 steps must take place for address auto-configuration to occur. Click each step number to learn more. If stateless auto-configuration is not desired, an administrator can manually assign a static address to a node. DHCP is also available. In IPv6, DHCP is known as stateful DHCP v6, and RFC 3315 defines it. Several reasons exist to configure DHCP v6. For example, you might want to implement a specific IPv6 addressing scheme across your network. You might desire dynamic assignment of IP addresses to DNS servers. In some cases, you might require dynamic updates to your DNS servers. For security reasons, you might want to exclude the MAC address as part of the IPv6 address. Note: DHCP v6 and DHCP v4 are independent and require separate configurations. 2 routers with a unique local IPv6 address assigned to their GE0/0/1.0 interface are displayed. Unique local addresses are similar to the concept of private addresses in IPv4. They are not expected to be routable on the global internet. Instead, they are routable inside a more limited area, such as a site or between a limited set of sites. In practice, applications can treat these addresses like global scoped addresses. Originally, IPv6 private addresses were defined as site local addresses using FEC0:/10, but were later deprecated on RFC 3879 deprecating site local addresses for concerns regarding their lack of uniqueness. The RFC provides details on the potential issues that result from this lack of uniqueness. Unique local addresses were specified later when the IETF community recognized the need to provide for private IPv6 addressing. The specifics are covered on RFC 4193 Unique Local IPv6 Unicast Addresses. These addresses have a high probability of global uniqueness. You use the Show Interface Terse command to verify interface status. In this example, you see the site local address defined in the previous screen, along with the unique local addresses that the configured interfaces generated and assigned. You use the Show Route Table INET6 command to verify the routing table contents. In the example output, interface routes have been added for both the site local addresses and unique local addresses. Initially, all data link layer addresses of any IPv6 neighbor are unknown. As shown here, you can use the ping utility not only to verify reachability, but also to learn the data link layer addresses of IPv6 neighbors. After the ping operation succeeds, R1's neighbor, or R2, is listed along with its IPv6 and data link layer address information. A multicast address is an identifier for a group of nodes. Unlike with any cast addresses, when a packet travels to a multicast address, all members of the multicast group process the packet. IPv4 defines multicast, but IPv6 has redefined and improved multicast. Broadcast packets are not routable, and every node on a subnet must process them. Multicast packets, on the other hand, are processed only by nodes of the multicast group. Multicast packets can also be forwarded over routers. In IPv6, ICMPv6 is used for multicast group management to optimize multicast traffic. This process is referred to as Multicast Listener Discovery, or MLD. Multicast addresses are identified by the high-order byte FF, or 1111, 1111 in binary notation. The following three types of multicast addresses exist, as defined in RFC 4291. Solicited node multicast addresses are for neighbor solicitation, or NS messages. All nodes multicast addresses are for router advertisement, or RA messages. All routers multicast addresses are for router solicitation, or RS messages. The Anycast address is a new type of address in IPv6, and RFC 2526 defines it. You can assign an Anycast address to multiple interfaces in a group. Multiple nodes might be responding with the same Anycast address, but the packet will travel only to one of the nodes. An Anycast packet travels to the nearest node based on the notion of distance determined by the routing protocols in use. Anycast addresses offer the potential for a number of important services. For example, you can use an Anycast address to enable nodes to access one of a collection of servers providing a well-known service, without manual configuration in each node of the list of servers. You can also use an Anycast address in a source route to force routing through a specific ISP, without limiting routing to a single specific router providing access to that ISP. A sample default static IPv6 route configuration is displayed. Use the Operational Mode command to view static routes in the INET 6.0 routing table as illustrated. A sample OSPF v3 configuration for two neighboring routers is displayed. Note that OSPF v3, similar to OSPF v2, uses a 32-bit router ID, or RID, which is defined under the Edit Routing Options hierarchy. Although you can dynamically select the RID from IPv4 addresses defined on the router, It is recommended that you always configure a RID. Most operational show commands used to monitor OSPF v3 are nearly identical to the commands used to monitor OSPF v2. The key difference is that you must replace the OSPF portion of those commands with OSPF 3. A number of common operational commands for both OSPF v2 and OSPF v3 for comparison are displayed. A sample ISIS configuration using IPv6 addressing instead of IPv4 addressing is illustrated. Note that other than the IP addresses, the ISIS configuration is the same for IPv6 and IPv4 environments. You can use the same operational show commands for ISIS in IPv4 and IPv6 environments. A sample BGP configuration is shown here. The BGP configuration for IPv6 is almost identical to the IPv4 configuration. The major difference is that you specify an IPv6 address for the local and pair addresses rather than IPv4 addresses. You use the same operational show commands for BGP in both IPv6 environments and IPv4 environments. The show BGP summary command for two IPv6 peers in different BGP groups is shown here. One method of transitioning from IPv4 to IPv6 is to use tunnels to span the IPv4 networks until all the intermediate routers have been upgraded to support IPv6. Tunneling requires encapsulation of the IPv6 packet within an IPv4 header. The new IPv4 packet is then forwarded across the IPv4 network to the other side, where the IPv4 header is removed and the IPv6 packet is either processed or forwarded. Many approaches to tunneling have been defined. The following four approaches currently show the most promise: IPv4 compatible addressing, configured tunnels, 6 to 4, and 6 over 4. Let us examine a case study. In this case study, you will learn how to implement an IPv6 over IPv4 tunnel. Click each tab to learn more. Let us examine some verification tasks for the preceding case study. Click each tab to verify the tunnel implementation and operation. You have reached the end of this module. In this module, you learn to describe some differences between IPv4 and IPv6. List IPv6 address types. Describe the IPv6 addressing format. Enable an interface for IPv6 operation. Configure and monitor routing for IPv6 environments. Tunnel IPv6 traffic over an IPv4 network.